Hello everyone. In this video we will discuss the properties of limits. There are many properties for which limits that can apply to limits. The first of which is the constant multiple property, which states that if you apply a limit as x approaches a to a constant multiple k acting on a function f of x, then the constant multiple can be simply withdrawn out of the limit and multiply the result of the limit as x approaches a on f of x itself. For example, the limit as x approaches 1 of 3x squared is equal to 3 times the limit as x approaches 1 of x squared itself. Notice how 3 was simply extracted from the limit. And then direct substitution can be applied to the limit as x approaches 1 of x squared to give a result of 3. Now, in practice, you would probably not do this since 3x squared is a polynomial and direct substitution could have been applied right from the start. But here's an example where that property does come in handy. We have in the first place the limit as x approaches 0 of sine of 3x over x. This is a 0 over 0 form. The problem with it is that although we know how to factor and we know how to rationalize and we know how to deal with fractions, this doesn't fit either of those possible techniques. I've chosen to multiply by 3 above and below in the first step, first of all because 3 over 3 is 1 and we do not alter the value of the function at hand. But most of all, I've created a divider, 3x, that replicates the angle inside the sine. So sine is acting on 3x, and I've created an equivalent 3x. This may remind you of the special limit forms that we saw in the previous videos. The only thing in the way now is the 3 at the numerator, which I have chosen to extract. So I'm using the constant multiple property. 3 at the numerator is extracted. 3 at the denominator I'm leaving because actually now we have the special limit form. And we know that this term between parentheses tends towards 1. Second property, or properties, are actually the addition and subtraction properties, which simply states that the limit of a sum of two functions is equal to the sum of the individual limits of these functions. And the same is true about their difference. For instance, the limit as x approaches 1 of 3x squared plus ln of x minus root of x can be split up into the individual limits as x goes towards 1 for 3x squared, for ln of x, and for the root of x individually. These can be computed, and the results are then tallied to give 2. Multiplication property says that the limit acting on a product of two functions can be replaced by the product of the two individual limits on these functions. If the original limit has x tending towards a, obviously we will apply limits as x tends towards a to both f and g individually. For example, if we had the product of 3x squared times ln x minus root of x with a limit forcing x to tend towards 1, we could compute the limit as x tends towards 1 on 3x squared, followed by a separate limit acting on ln of x minus root of x, where x tends towards 1. And the result of each limit can then be multiplied. Once again, you may have chosen to do this last problem by direct substitution directly, which is not as easy in this example, where the limit as x tends towards 0 for tan of x over x at first shows a 0 over 0 form. So as a first step, I have chosen to rewrite tan of x as sine x over cos of x. Perhaps you are wondering why make that choice. That will show up later. Some of you may have the intuition to think of how we could pair up now the terms in these two fractions. Second step, I have just manipulated the numerator and denominator's terms, so I've regrouped them in a different manner. So I've collected sine of x over x as a first fraction and left 1 over cos of x as a second. This is now a product of two functions, and I'm going to use the property of multiplications in limits to separate the limits into two pieces, one acting on sine of x over x and one acting on 1 over cos of x, both where x tends towards 0. The second limit in this product tends towards 1 by direct substitution. The first limit tends towards 1 because it's a special limit form. So once again, it's a matter of recognizing forms that we can use. Same goes for the division property. So the limit as x tends towards a of a quotient can be replaced by the quotient of the individual limits as x goes towards a on f and on g respectively. For instance, the limit as x tends towards 1 of the quotient 3x squared over ln x minus root of x can be replaced by individual limits on the numerator and denominator, who can then be calculated by direct substitution. This is also true about the original quotient that could have been done by direct substitution. Here's an exception to that. The limit as x tends towards 0 of sine x over e to the x minus 1 is a 0 over 0 form at first, and therefore cannot be computed by direct substitution. Those numerator and denominators may seem familiar. In fact, all that's missing for both to fit a special limit form is a division by x. Now luckily, dividing both the numerator and denominator by x does not change the fraction, as they both maintain the same quotient, the same ratios. Here is where I will now use the property on divisions. So I've separated the limits. So here I'm dividing by x to maintain the equality of the outcome. Here I'm using the property of the quotient of limits that replaces the limit of the quotient. And actually individually, the numerator and denominator are both special limit forms that tend towards 1. Finally, it's a property of composition of functions. So if f is a continuous function, then the limit as x goes towards a of f of g of x can be replaced by f calculated at the limit as x goes towards a of g of x. In other words, you can evaluate the limit on the inner function and apply function f to the outcome of that limit afterwards. This is only true if f is continuous. For example, here we have the limit as x tends towards 1 of ln of x squared minus 1 over x minus 1. Ln functions are continuous functions within their domain. Currently, the problem is not the ln, it's the content of the ln, which has a 0 over 0 form. So the property of continuous functions allows us to insert the limit inside of the ln. So now we have a limit with a 0 over 0 form, but these are polynomials that can be factored. The factors that are common can be eliminated, and then direct substitution can be applied inside this limit to give 2, so ln of 2 would be the outcome.